So the next topic in the unit is going to be pressure after density. And these are the three learning objectives. One, you're going to be able to know and use the following relationship. Pressure equals force divided by a unit area. Understand that pressure at a point in a gas or a liquid which is at rest is acting equally in all directions, and know and use the relationship of pressure difference equals height times the density of that particular liquid times the force due to gravity. Okay, so the first thing we will look at is pressure and the equations associated with pressure. So what is pressure? Well, pressure is a force exerted over an area. Well, P equals F divided by A, where F is in newtons and A is in meters squared. Here we go. So force is in newtons and area is in meters squared. And pressure, the units we will use is pascals or PA. Also, you need to know that force therefore equals pressure times area, and area equals force divided by pressure. So you have to be able to rearrange the equation. Okay, and we can of course use a equation triangle for that, with force at the apex and pressure and area at the bottom. You'll have to note, of course, that 1 Pascal is the same as saying 1 Newton per square meter, or newtons per meter squared. So let's give an example to see if you've really understood this. So pause the video now and try and calculate the pressure exerted by a force of 200 newtons when it is applied over an area of 4 meters squared. Okay, so what you should have used is, of course, the correct equation, which is pressure equals force divided by area. We have a force of 200 newtons and an area of 4 meters squared. So we plug those into the equation, and you should have an answer of 50 pascals. Question 2. Calculate the force exerted by a gas of a pressure of 150,000 pascals on an object of a surface area of 3 meters squared. So again, pausing the video, see if you can work it out yourself and see if you get the correct answer by pressing play later. Okay, so again, breaking down the questions, we're told the pressure is 150,000 pascals here, and an area of a surface is 3 meters squared. So pressure equals force divided by area. So again, we can rearrange the equation now, where force is going to be the pressure times the area. We plug in the numbers and you should get an answer of 450,000 newtons. Third question, calculate the area that will experience a force of 6,000 newtons from a liquid exerting a pressure of 300 kilopascals. Okay, so again, pausing the video, seeing if you get the correct answer, or seeing if you get an answer, and comparing it with the answer that I will soon give. Right, so again, the force is going to be 6,000 newtons, and we have a pressure of 300 kilopascals. Be wary of that. So again, the basic equation is pressure equals force divided by area. We rearrange the equation so it becomes area equals force divided by pressure. So it will become 6,000 newtons divided by 300 kilopascals. Remembering, of course, that 300 kilopascals will be equal to 300,000 pascals. So you have to convert kilopascals into pascals before you do the final calculation, which should give you an area of 0.02 meters squared. So as an activity, basically write this up in your booklet, okay, and complete the missing forces, areas, and pressures. And once you've done that, replay the video and see if you get the correct values. Okay, so there we go. We've got 5 pascals for pressure, 20 meters squared for the second example, 400 newtons for the fourth or the third example, 100 kilopascals, remembering of course kilopascals, unit for the second to last example, and for the last example, 2 millimeters squared. Be careful, of course, for here, remembering you've got to convert millimeters squared or centimeters squared into meters squared, and megapascals and kilopascals into pascals. So here is a question about the pressure exerted by a block. Okay, so it's kind of combining the ideas possibly of density. The metal block shown opposite has a weight of 900,000 newtons. Okay, that's the force. Okay, because weight is a force. Calculate the maximum and minimum pressures it can exert when placed on one of its surfaces. Okay, so looking at the minimum possibility and the maximum possibility. So pause the video now, write what you think the answer is, and then play the video to see if you're on the right track. Okay, so I've already kind of broken down the question already. So the force is going to be 900,000 newtons because weight is a force. And now it's just about choosing which area is the biggest for that particular block and which area is the smallest, because the one with the biggest area will have the least pressure and the one with the smallest area will have the biggest pressure. So maximum pressure occurs when the block is placed on its smallest area surface. Okay, smallest, which is the 2 times 3 meters. So we just use the equation, pressure equals force divided by area, plug in the numbers, and we get a pressure of 150,000 pascals. For the minimum pressure, this will occur when the block is placed on its largest surface area, which will be the 3 times 5. Okay, this one, here, and here. So again, we use the correct equation, pressure equals force divided by area. We plug in the numbers, and we should have a minimum pressure of 60,000 pascals. Hopefully you got that correct. Okay, so then this next slide, what we're going to do is give some examples of some pressures in real world situations. So what you should do is pause the video now, go away and do these research questions for yourself. Okay, look up these numbers, and then replay the video to see if your numbers match up to the numbers that I have found. And then we're going to discuss these numbers and what they actually really kind of mean. Okay, so the first one, once you've done the activity, is space. Now space has a pressure of 0. Okay, that's why you would kind of, well, not really explode in space, but kind of gently seep out from all your orifices. All your liquids would gently seep out of your orifices, because you have a high pressure inside your blood cells, for example, inside your cells, and there'd be no pressure on the outside, so there'd be pressure exerting on the walls of your cells, which isn't particularly nice. They just eventually slowly leak out. The air pressure on top of Mount Everest is about 30,000 pascals, and compare that to the air pressure on the ground level, or sea level, it's 101. So it's about a third less. Okay, so it's about a third less on top of Mount Everest. Okay, so because of that, the level of oxygen on top of Mount Everest is about a third of what it should be. So it should be about 7 to 8% oxygen. Okay, so that's why you have to use air tanks if you want to get to the top of Mount Everest. Typical tire pressure is about 180,000 pascals. The pressure 10 millimeters below the surface of the sea is about twice the pressure on which we're experiencing here at school. Okay, so that's kind of intimidating, and that's why when you're going up, from this 10-meter surface, below the surface, you need to take your time, because if you don't equilibrate the pressure, then the nitrogen gas, which is in the air, which is trapped in your cells, will push against your cell walls, cell membranes. We are human after all. Cell membranes, and cause damage, and it's called the bends. And the estimated pressure, therefore, if you went down to try and find the bottom of the wreck of the Titanic and find Rose's necklace, that's your thing, that would be 41 million pascals. Okay, that's a massive amount of pressure. That's why you'd have to use a submarine. Okay, and you couldn't do it just by diving. It'd be crazy, it'd kill you. Okay, so there's some examples of pressures and some numbers of pressures to kind of give you an idea of what the values mean. So the next thing we will look at is how we can calculate the pressure exerted by a person on the floor. the first thing you do is weigh the person in newtons. Now notice that we're measuring in kilograms, we're measuring in newtons. So we're going to find a way to convert the weight of the mass of a person into the weight of the person. Okay, and newtons are of course a measure of force. So force equals the mass times G. Okay, so you've worked out the mass from the balance. You've got to multiply it by G. So what is G? Well, G is the force associated with gravity, which will equal 10 newtons per kilogram. Okay, so for every kilogram, you exert 10 newtons. So with that information, because now you've got basically force equals your mass times 10, you draw on a graph the outline of the person's feet or shoes. You use the graph paper then the outlines anyway on the graph paper to calculate the area of contact A with the floor in meters squared, with the note that 1 meter squared equals 10,000 centimeters squared, and finally calculate the pressure in pascals using pressure equals force divided by area. So typical results for you, the weight of the person should be around about, well, for you to discover, about 500 newtons for you because you're about 50 kilograms. Okay, so it'll be 50 times 10. The outline area of both feet in centimeters should be for you about 60 because you've got reasonably small feet. Outline the area of both would be about 0.06, and the pressure therefore would be about 500 newtons, which is divided by 0.06, and that will give you about 8,300 pascals. Okay, we'll do this in class as well to see the variety of forces being exerted by you and different pressures that you exert on the floor. So why off-road vehicles have large tyres or tracks? So this is an example of an off-road vehicle which has large tracks, or tyres in this case, and tanks obviously have tracks. In both cases, what you're doing is you're increasing A, okay? So we already know that pressure equals force divided by area. Now, these guys are pretty heavy, okay? So that number is going to be quite large, but you also want to increase this number here to balance out the force. That way the pressure is reduced, so you're not sinking into the mud, which is probably the next part of the slide, because as I've said, pressure equals vehicle weight divided by area. So low pressure means that it doesn't get stuck and sink, basically. So the next thing we're going to look at is how gases exert pressure, which we touched on briefly when we look at the difference between oxygen pressure, well, it's air pressure, on top of Mount Everest compared to at sea level. So a gas consists of molecules in random constant motion. And when a molecule collides with a surface, it reverses direction due to the force exerted on it by the surface, okay? The surface or the inside of the gas container, if it's a container holding the gas. And the molecule is in turn exerts a force back on the surface. So the force that's being exerted back on the surface is what we experience as pressure. And the pressure exerted therefore by the gas is equal to the total force exerted by the molecules on a particular area on the surface divided by that area. So in terms of air pressure at the top of Everest compared to at sea level, there's less particles. So because of that, there's less collisions, less force being exerted. So it means that the pressure is reduced. Okay, so there we go. Pressure equals force divided by area. So further up, okay, the force goes down because you've got less particles, but the area stays the same. Okay, and if you heat a gas in an enclosed container, then obviously the pressure is going to go up because what you're doing is you're increasing the energy, the movement of the particles. So the force is going to go up because you're increasing the energy the particles are moving at. In terms of pressures and liquids and gases, the pressure in a liquid or gas at a particular point acts equally in all directions. Okay, what does that mean? It just means at the same depth, Okay, the pressure the liquids are exerting is the same in all directions, all three dimensions. Okay, but as you go down, then the pressure is going to increase, and as you go up, the pressure is going to decrease. So the pressure in a liquid or gas increases with depth. Okay, so here we have the pressure at the top of this particular container. When you release the first top valve, you can see that it's kind of just flopping down. The second one gets released, there's a little more pressure being exerted, so that means there's more force, which the water is being pushed out of the container. And finally, the pressure is quite high at the bottom, so the force pushes the stream of water furthest. Okay, the pressure of a liquid increases with depth. So there is an equation, of course, between pressure, height, and depth, and this is the pressure difference is equal to the height times the density times g, which is the acceleration due to gravity. Okay, or P equals h times rho times g. And the units in height or depth are meters, density is kilograms per meters cubed, and gravitational field strength is newtons per kilogram. And the pressure difference is in pascals, which we've already done. So let's finish off with a few questions. Calculate the pressure increase of the bottom of a swimming pool of a depth of 2 meters. Density of water is 1,000 kilograms per meters cubed, and G is 10 Newton kilograms. So pause the video now, see if you can come up with an answer, and then compare it to the one that I will provide once you press play. Right, so pressure difference equals H times rho times G. You plug in the numbers and you get the answer of 20,000 pascals. Quite a lot of pressure. Okay. Question 2. At sea level, the atmosphere has a density of 1.3 kilograms per meters cubed. So 2 points. Calculate the thickness or height of the atmosphere required to produce an average sea level pressure of 100 kilopascals. And why is the actual height much greater? And G is given, of course, as 10 newtons per kilogram. So again, see if you can work it out for yourself. If you get stuck or you've found the answer, or you think you've found the answer, press play and see if you are correct. Right, so again, the equation we're using is pressure equals H times rho times G. You rearrange the equation to become the height equals the pressure divided by rho times G. Okay, this is why algebra is important, which will be 100 kilopascals divided by the product of 1.3 times 10, which will equal 100,000 divided by 13, which will equal about 7.7 kilometers, but you'll get the answer in meters, 7,692 meters. Okay, so that's part A. Calculate the thickness of the atmosphere, about 7.7 kilometers. But why is the atmosphere actually greater than 7.7 kilometers? Well, the reason why is the real atmosphere density decreases with height. Okay, because we've already looked at that when we looked at the difference between the air pressure at the top of Everest and at ground level. You can see that the amount of particles is decreasing as you go up Everest. So therefore the atmosphere extends at least to about 100 kilometers due to this fact, that the density is not the same all through the atmosphere. So just to complete, the paragraphs here with filling in the correct words. So we'll just do it together. So pause the video now, complete the sentences, and then we'll go through it. So pressure is equal to force divided by area. Pressure is measured in something called pascals, where 1 pascal is the same as 1 Newton per meter square. The pressure of the Earth's atmosphere at sea level is approximately 100,000 pascals, and pressure increases with depth below the surface of a liquid, and underwater the pressure increases by 1 atmosphere for every 10 meters of depth. So in terms of density and pressure questions that you could do for revision, here are a number. Give equations for the density and explain how density of a regular solid can be found. Give the equation for pressure and explain why it is advantageous for a camel to have large feet. Question 3, state the equation showing how pressure varies with height in a liquid or gas, and therefore draw diagrams showing how a can of water can be used to demonstrate this principle. And finally, there's a few online simulations through PhET, through density, buoyancy, balloons and buoyancy, and there's also some density labs. Okay, so that is pretty much it for pressure, and we're going to move along in the next topic and explore other principles.